Natural disasters are a common phenomena to India as they are to other parts of the world. They are in the form of earthquakes, cyclones, floods, droughts, epidemics, etc. But the earthquake is the deadliest since it cannot be predicted.
Latur earthquake of 1993 and Jabalpur earthquake of 1997 are a few of the recent disasters in India. Disaster means injury, death, and destruction. But it is possible to reduce the impact of an earthquake through the use of scientifically based building technologies. In India, most of the north and parts of the west and recently identified central, stretching down to northern Karnataka, are prone to earthquakes of a moderate to high intensity. There are tens of millions of houses that are vulnerable to their might. The existing houses that are not made to withstand an earthquake could be strengthened or retrofitted. It increases people's chances of survival and reduces the loss of properties. It costs less than a fifth of the cost of constructing a new house. Hence, it is the most viable option for ensuring one's safety.
It is, however, important to build people's confidence in the ways of improving the strength of their houses, existing or new. But a common man does not understand the complicated engineering principles of formulas. For him, seeing is believing. This is why we have carried out a series of 4 simple demonstrations to show how a properly built house having earthquake resisting features performs when subjected to the horizontal forces of an earthquake as against a house that is improperly built or is lacking in such features.
The demonstration consists of 2 half-scale houses built on a 3 meter by 5.5 meter reinforced cement concrete platform that is placed on rollers. The whole assembly is subjected to horizontal shocks with the help of a tractor. The shocks are measured with the help of accelerometers attached to both the houses. The first test consists of a traditionally built house of Latur area with 24-inch thick random rubble masonry walls in mud mortar and 18-inch thick mud roofing on wooden understructures supported on all the walls. The second house is identically built but with only 8-inch thick mud roofing. The walls have been retrofitted with the cast in situ reinforced concrete bond elements serving as through stones and a 4-inch thick reinforced concrete band in the walls just under the roof level. The roof has been retrofitted with in-plane diagonal timber bracings on the underside of the roof with the joists tied to the band. The test was started with mild shocks to begin with. The shocks alternated from the north and the south ends. The intensity of the shocks was gradually increased. The first 6 shocks caused no damage to the structures. In the 8th shock, vertical cracks developed in all 4 corners of the ordinary structure, indicating the separation of the walls. The impact number 10 and 11, vertical cracks developed in all the corners of the improved structure, and those in the ordinary structure widened. In impact number 12, in the improved structure, a horizontal crack developed across the full length of the south wall at approximately mid-height. In traditional structure, cracks opened up much more. In impact number 13, in the ordinary structure, most of the east wall and the east half of the south wall collapsed. The force from the tractor was approximately 20 times the minimum earthquake force specified by the building code. In impact number 14, in the ordinary structure, most of the west wall's exterior face delaminated and north wall went out of plumb. In the improved structure, the cracks widened further. The results clearly show that proper retrofitting can greatly improve the chances of survival of the occupants of a traditional stone and mud house. Since the Latur earthquake, the people of that area feel safer in the use of lighter materials in house construction. As a result, they are opting for bricks in place of stones since they perceive bricks as lighter and hence safer. The second test was planned with an objective of rebuilding people's confidence in the seismically improved stone house as against what the people are building with bricks. The seismically improved house has 15-inch thick walls of better quality random rubble masonry in mud mortar, having proper interlocking of stones, breaking of joints, and regularly placed through stones. A 3-inch thick reinforced concrete band is installed at lintel level and corner strengthening at mid-height in each corner. The corrugated galvanized iron roof is anchored with J-hooks. The wall plate frame is tied diagonally with two 3mm GI wires. The commonly built brick house consists of 13.5-inch thick brick walls in mud mortar with the exterior face finished in cement plaster. The roof is corrugated galvanized iron sheet simply put on the walls and a midspan purlin. Impacts 1 and 2 registered no visible damage. In the third impact in the ordinary structure, shear cracks developed in the south wall. In the improved structure, a diagonal crack developed in the west wall. In subsequent 4 impacts, the cracks in both structures widened and deepened. The severity of impacts kept increasing. In impact 8, all cracks widened considerably. Along the diagonal cracks at the northwest corner of the improved structure, a triangular chunk of wall visibly separated out. In impact number 10, in the ordinary structure, the middle 20 inches of roof load wall along the north side collapsed. All cracks widened further. In impact number 11, in the ordinary structure, east half of the north wall collapsed. Cracks widened further in the improved structure. The force from the tractor was approximately 10 times the minimum earthquake force specified by the building code. In impact number 12, in the ordinary structure, all the walls collapsed excepting the east wall. The improved structure, although damaged, stood up. The result clearly shows that a properly built stone house having earthquake resisting features is safer than a brick house that the villagers build. The use of full band at mid-height can significantly reduce the damage.
The third test was carried out to compare the performance of an improperly built house in cement mortar against a properly built house in mud mortar having various earthquake resisting features.
This is the third of the 4 test series. Here the building on the right is built with burnt bricks, as most of the people do, using cement mortar, and it has CGI sheet as a roofing. The walls have been built typically the way the masons do locally. The CGI sheets are not anchored, they are simply placed on top of a purlin and the walls, and on the top there are load walls made of brick and cement mortar on three sides. This particular building is what we call an improved brick masonry building. The difference between this building and the other is that this is built with brick and mud mortar, and it has two bands. There's a band at lintel level, which is a reinforced cement concrete band. The band at mid height consists of two layers of chicken wire mesh. The chicken wire mesh is embedded in mud mortar. The roofing consists once again of CGI sheets, but the sheets are anchored to the purlin and the wall plates. The wall plates are anchored to the walls, and underneath the CGI sheet we have diagonal ties using two 3 mm GI wires.
After the first two impacts resulting in no damage, the third impact caused a diagonal crack across the west wall of the ordinary structure.
Here in this third test, we can see that the walls which are parallel to the direction of loading suffer shear crack. And this crack is very clear, it's a diagonal shear crack, and it is going through and through.
In impact 4, in the north wall of the ordinary structure, vertical shear cracks developed at its both ends. The diagonal crack in the west wall became through and through. In the improved structure, only a few minor cracks showed up. In impact 5, in the ordinary structure, most of the north load wall collapsed, and the portion of the southwest corner of the west wall below the roof also collapsed.
So now this building, traditional building, has now collapsed with the front wall completely coming down. You can very clearly see that the front wall, the top leaning forward, it has behaved flexurally, practically like a cantilever, with all the cracks which had developed earlier. I think this one was the one enough to break this wall. And even here, the shear walls, there is a significant movement of one block because this crack was already there. So the fifth shock, this portion has moved forward, and the other wall also has developed cracks. But now it has developed cracks slightly at a lower level, maybe because the top portions have cracked so much, only the lower portion took the remaining load in the last shack. This improved building is performing exceedingly well. Although few cracks have occurred, it's interesting to notice that the shear walls have not had any cracking. The excellent tying at the three levels, roof level, lintel level, and the mid-wall level, we find that the shear cracks have been practically eliminated. And you now notice vertical flexural cracks, but here we are noticing only vertical cracks. This also may be attributed to the excellent tying in the horizontal direction.
In impact 6, in the ordinary structure, half of the south wall collapsed. In impact 7, all of the north wall, barring that near the ground, collapsed, and most of the west wall also collapsed. The improved structure showed only a few minor cracks. In impact number 8, the ordinary structure totally collapsed. One more impact was given to the improved structure, which continued to show only minor damage. The most visible damage was near the base at the southwest and southeast corner. The test was discontinued at this point.
Friends, just now the test program has been completed, and we have here the traditional building completely demolished due to the 9 shocks it received, and the improved building is intact, and a very unusual kind of failure has taken place in the sense that the building is separated from the table. We stopped the test here because it is no longer meaningful to continue the test. The building has, I can say, has passed the test completely. Simple thing like a chicken wire mesh at the sill level has done a wonderful job of giving band, behavior of a band. Probably one should also explore whether it is necessary to provide steel for banding. Even chicken mesh itself may provide, or thin GI wires themselves may provide the kind of banding that the reinforced concrete has been doing.
This test also demonstrates the outcome of the ignorance that prevails among the people about the correct ways of using cement with bricks, which involves thorough soaking of bricks in water prior to construction and also curing of the construction for at least 20 days.
And it's also gratifying to note that a building using only mud mortar, just the additional feature of tying at 3 levels, has performed much better than a building in cement mortar.
Technology demonstrations carried out by various groups after the earthquake in Latur area are affordable only to the rich, but the masses cannot afford them. Masses continue to build with adobe or the simple hand-molded sun-dried mud blocks. There are simple and cheap ways to increase the earthquake resistance of mud houses so that the poor also can ensure their safety against an earthquake.
The fourth test is being carried out with an aim of demonstrating the effectiveness of various earthquake resisting features in an adobe house against an earthquake. The house on my left is a traditional house consisting of walls made of traditional adobe. During the construction of the walls, the 4 corners were constructed first, followed by the construction of each wall one after the other. The corrugated galvanized iron roof is placed on the walls and also supported at mid-span on a purlin and is held in place with the load wall along the 3 edges as well as stones placed on top of it. The house on my right is the improved house. The walls of this are built with adobe, either consisting of a V notch in the middle or having corners which are cut off. The walls were built simultaneously and are reinforced on inside and outside with 3 mm GI wires. It has a bamboo band at lintel level as well as a layer of chicken wire mesh at the mid-height. The corrugated galvanized iron roof is anchored to the wall plate with J-hooks. The wall plates in turn are anchored to the wall with GI wires.
After 3 mild impacts, the traditional structure developed several through and through cracks. The improved structure got few superficial cracks. The 4th impact, which was more severe, made the cracks much wider in the traditional structure. Parts of roof parapet were left on the verge of collapse. In improved structure, some damage became visible at roof level in the unreinforced portion.
The traditional building, although it did not collapse, is inching towards collapse, and we can see one of the parapets falling apart, showing that the various parts are coming apart. The cracks have become wider and it is just in a state of incipient collapse.
The sixth impact left gaping holes in the traditional structure, with one corner breaking off and the other left on verge of collapse. In the improved structure, small parts of roof load wall collapsed. This shock was approximately 16 times the force specified by the National Building Code. In the seventh impact, the south wall of traditional structure collapsed. Cracks became much wider. In the improved structure, further damage was seen in roof load wall and at wall base which are not reinforced. This test clearly shows that high vulnerability of mud structures can be greatly reduced by proper tying and reinforcing with relatively cheap materials like bamboo, chicken wire mesh and galvanized iron wire.
Now with the 8th shock, the improved building is showing a little more damage. And what is interesting here to observe is that there are two weak points in this building and these weak points are showing up in the 8th test. Firstly, as mentioned earlier, in the corners where there is inadequate tying, the bricks are coming loose and the bottom of the building is not able to transfer the load. Secondly, we find in this longer wall, the middle portion, the spacing between the vertical wires is rather large. And because of this, you find that the portion of the wall in between is suffering greater damage because one vertical wire is missing. It very clearly shows that when the earthquake resistant feature is inadequate, the building starts showing damage at that particular feature. I have now witnessed two tests of building models subjected to horizontal shocks conducted by ASAG here at Latur. And also after studying the earlier two test reports, I find this method of testing a fascinating approach to develop earthquake-resistant designs of buildings. Of course, people may argue that this kind of a shock test is too simple. It may not reproduce the full complexity of earthquake ground motion. And there are scientists who say that to do proper testing, you should simulate the earthquake properly in a shake table and carry out a full-fledged seismic testing. But I personally feel that this kind of testing has a very important role simply because the full-fledged earthquake simulation is a very expensive proposition. There are very few places in the world where such facilities are available, and an average engineer who wants to upgrade a simple building design simply cannot have any access to such facilities. And in this context, especially for building simple buildings of poor people in rural areas, we need to develop an appropriate testing mechanism which is reliable in reproducing failure-resistant behavior in building models. And I personally feel this is very satisfactory for two reasons. Although each shock may not simulate an earthquake, one can argue that a series of shocks can cumulatively reproduce the kind of damage produced by an earthquake. And this is very clearly brought out by the kind of damages of traditional building models shown in these tests. The failure models here, which we saw, is very similar to what happens to buildings during earthquakes. And on this reason, we can use this as a powerful tool to test earthquake-resistant features. Any new concept in earthquake-resistant design can be tested through a model here at a fraction of the cost of putting up actual structures. And I think it's here very quickly one can go through a variety of ideas and validate them before implementing them in the field. And I think this can be a powerful educational tool for engineers and architects. It can be a a powerful tool to educate people about alternative technologies. I think, I hope these tests number of such tests will increase, and they will increase in their reliability and sophistication, and they can provide very valuable information to engineers and architects in developing some designs.